Welcome back to the 15th video about the full fly-by-wire electric outboard project. In the previous video, we designed and implemented our RS-485 bus hardware. Card here, link in the description. We also coded some software to demonstrate that the communication between a dummy master and our fly-by-wire motor controller actually works. But now it's time to design and implement a proper RS-485 protocol. Enjoy! When we designed the RS-485 hardware in the previous video, we had a clear sequence of decisions we had to make. And some of these decisions implied what the next decision would be. When it comes to designing a communication protocol, there is no clear sequence of decisions. So this video will be necessarily a wee bit unstructured. So what's our starting point? We have of course an RS-485 bus, and meanwhile we know that it's a half duplex bus and it runs at a speed of 1 megabits per second. Let's first have a look at the data our controller and bus master has to send to our two motor steering controllers and what data the two motor steering controllers are sending back to our bus master. And then we can make an educated guess what data the bus master is sending to the non-existent battery monitors and what data the battery monitors will send back to our bus master. Starting with the data transferred between the motor and the master. So the master sends to the motor, of course, the throttle setting. We already implemented that between -100% and +100%. We can put that into a single byte. Then in the future we will have to send the tiller respectively rudder setting, let's say between -90 degrees to +90 degrees. That's another byte. The motor sends back to the master the battery voltage between 0.00 volts and 30.00 volts. That's 2 bytes. And then the current it's drawing between 0.00, yeah, I'm still optimistic here, to 50.00 amps, another 2 bytes. Then the temperature inside the housing between -50 degrees to +100 degrees C. Yeah, I'm just guesstimating here, but that should fit into a single byte. Then we have our intrusion detection for different sorts of waters. That was 2-bit. That of course fits into a single byte. And it would be good practice to send back also the throttle and the tiller setting. That is the actual throttle and tiller setting. So 2 more bytes. And yeah, I still have in the back of my head that we can do an RPM measurement. And if I read the internet right, RPM could be between 0 and 1350. Yeah, we don't get that resolution, so we deliver something between 0 and 135, so that should also fit into a single byte. In addition, the master-to-motor messages must contain an address. Yeah, we have 2 motors on the bus and 2 battery controllers. So that's another byte. And of course, we will add a cyclic redundancy check to our messages. So yet another byte. But I don't think we need to add a message type. There's only a single message type the master is sending to the motor, and there's probably also only one message type the master will be sending to the battery monitors. So we end up at a total of 4 bytes for the master to motor messages. It's good practice for slaves like the motor to include their own address in replies to the master. So we have here also that address byte. And of course, the slave messages will also contain a CRC byte. And again, we don't need a message type. There's only a single message that a motor can send back to the master. So here's the total of 11 bytes. Assuming we're using a UART setting of 8 data bits, even parity and 1 stop bit, we need 11 bits to transfer a single byte. Remember, there's also a start bit at the front. So to transfer our 4-byte message from the master, we need 44 bits on our bus. And at 1 megabits per second, that means we need 44 microseconds to transfer that message. Assuming we are using the same UART settings for our motor slave, like we had a choice here, we need 121 bits to transfer that 11-byte message, which takes 121 microseconds at 1 megabits per second bus speed. Now let's talk about the data flowing between the battery monitors and the master. To be honest, I have no idea what actual data a master could send to a battery monitor besides an empty message requesting the battery data. The battery monitor can of course send a lot of data back to the master when requested. First, the voltage and the current, like a motor controller does, with the exception that the current starts here at minus 50.00 amps. We can charge a battery after all. So that's 2 times 2 bytes. If we do some colorimetric calculations, we could also return the actual charge state of the battery. Let's say between 0 amp hours to 200 amp hours. That's another byte. We can also return 2 temperatures. First, the temperature of our electronics in the watertight case, and then the temperature of the battery itself. Same ranges like for the motor electronics temperatures, so 2 more bytes. Finally, we can have 2 intrusion detections for water. 1 for the electronics case and 1 for the compartment where the battery is in. So that's 2 times 2 bits. That still fits into a single byte. Makes a total of 8 bytes. And of course, all that protocol overhead comes on top of everything, but I don't think we need to talk about that again. Anyway, take all that information with a grain of salt, because we haven't implemented our battery monitors yet. Now, why was I so keen to calculate the times we need to transmit our master to motor and motor to master messages? And let's round them up here to, let's say, 50 microseconds for master to motor and 150 microseconds for motor to master. It all comes down to timing. You see, when you turn the wheel at the controller, you don't want a noticeable delay between your tiller, respectively rudder responses between the 2 motors. That would be more than annoying. So, let's have a look at a typical communication sequence between our master and our 2 motors. And I called them motor 0 and motor 1. Let's assume the master first sends a message with new throttle and tiller settings to motor 0. That's 50 microseconds. Then we give the whole system 500 microseconds time to process the whole stuff. That's 10,000 instructions on an Arduino Nano Every. And after that, motor 0 can reply with a status message to the master. Another 150 microseconds. Again, 500 microseconds for processing and then the master can send a second message with the throttle and tiller settings to motor 1. Again, 50 microseconds, and the rest is the same. 500 microseconds processing, 150 microseconds for the status message back from motor 1 to the master, and at the end another 500 microseconds processing. The whole sequence will take 2.4 milliseconds, and the delay between motor 0 and motor 1 will be 1.2 milliseconds. The human eye has a time resolution between 33.3 milliseconds, aboutish 30 Hz, and 40 milliseconds, 25 Hz. And that 1.2 millisecond delay is an order of magnitude smaller. So you won't be even able to see the delay between motor 0 and motor 1. That is, we're golden. Now let's decide if we want to use fixed length messages or variable length messages on our bus. When it comes to the ease of implementation, fixed length messages are of course easier to implement than variable length ones. In regards to bandwidth efficiency, variable length messages are of course more efficient than fixed length messages. As we have seen, a message from the master to a motor takes up 4 bytes. If we would use variable length messages, a message from the master to the battery would only use 2 bytes, just the battery address plus a CLC byte. Meaning, with variable length messages, we could save 50% of the bandwidth. While if we used fixed length messages, we would have a 100% overhead. We also saw that a message from a motor slave back to the master is 11 bytes long. And a message from a battery slave to a master could be just 10 bytes long if we used variable length messages. Meaning variable length messages would save us 9% of bandwidth, or with fixed length messages we would have a 10% overhead in that case. But remember, a full communication cycle between the master and the 2 motors is only 2.4 milliseconds long, and of those 2.4 milliseconds, only 400 microseconds are really bus activity. And we can safely assume that a communication cycle between the master and the 2 batteries would look about the same. So in the end, we have our bus only occupied less than 5% of the time if we continue to use a 100 millisecond update cycle on everything. Meaning the gains in bandwidth efficiency we would get with variable length messages are not worth the effort. So we will go with fixed length messages. Onwards to the dreary part, the code. I have here a new file, protocol.h, that will be included by our dummy master and our full fly-by-wire electric outboard. And it's part of an empty sketch, okay? It starts with the usual, if not defined, define stuff of an .h file. Then I have here an enum RS-485 slave address, just a byte, where I enumerated all our future slaves. Currently, we only have the motor 0 with the address 0. Then I have here some constants for the RS-485 serial communication. First, the serial speed, 1 megabits per second. The serial config I will be using, so a serial 8 even parity 1 stop bit. And I also have here a constant that says, okay, a single word on my serial line will have 11 bits. Then we have a function RS-485CRC, which calculates the CRC of a byte array of a certain size. It's a copy and paste of the same function from my MLX9363 tri-axis magnetic sensor code. Links in the description, so I will skip over it. Then we have the Union RS-485 master transmission, which contains the data transmitted from the master to the slaves. And it's a union, so I can either address it as a byte array for the serial stuff, so 4 bytes, or as a structured message. And the message starts with the slave address and it ends with our 8-bit CRC. And in between we have a union data that can either be a struct for a motor slave or a struct for a battery slave. Please note the struct for the battery slave currently only contains 2 unused bytes, while the struct for the motor contains a signed 8-bit integer for the throttle value between -100% and +100%, as well as a signed 8-bit integer for the tiller position, so -90 degrees to +90 degrees. That is followed by a Union RS-485 slave transmission for the data transmitted from the slaves back to the master. Same principle. First we have a byte array here, this time 11 bytes, and then the message. And the message, of course, starts again with the slave address, and at the bottom, you have to believe me, is the CRC. And we have the union data, 1 struct for motor slaves, 1 struct for battery slaves. Again, all bytes in the battery slave are currently unused. In the motor struct, we have an unsigned integer 8 status, which currently only contains the intrusion bits. Then we have again a throttle value and a tiller value, like in the master message. Then we have an unsigned integer 16-bit for the voltage. The range is here between 0 volts and 65,535 volts. So least significant bit is here 10 millivolts, giving us a range between 0.00 volts and 655.35 volts. Not that we ever need that, but anyway. We have a signed integer current. Yeah, remember, batteries can be charged, and I want to use the same current format everywhere, going from -32,768 to 32,767 in 10 milliamp steps. So we can display or transmit currents here between -327.68 amps to +327.67 amps. And then we have a signed 8-bit integer, a temperature, for temperatures between -128 to 127 degrees C, and finally still have to implement that, if it's possible, an unsigned integer 8 RPM between 0 and 255, and that's in 10 RPM per minute steps, so between 0 and 2550 RPM. And here at the end you can actually see it really contains the 8-bit CRC. Then I have here 2 macros. First, a CRC transmission that just calls the RS-485 CRC function with a transmission bytes and the size of that byte array -1, calculating, of course, the CRC of the byte array. And then I also have a macro size here, which just gives me the size of the byte array. All that unstructured stuff above really belongs into a parent class for the following 2 classes. The first being the RS-485 master class. And here the standard constructor is deleted, and the real constructor gets as an argument a reference to a hardware serial and an unsigned integer 8, the data enable pin for our transceiver. And with those, I enable some private member variables. Then we have a begin method that initializes our data enable pin and our USART, like we did in the sketch for the master. And before we go through the rest here, let's have a look at the private member variables. There we have our hardware serial and our unsigned integer 8 data enable pin, which are initialized by the constructor, and we already used them in the begin method. But we also have two arrays here, currently of the size 1, because we only have one slave. But in the future we will have more slaves, up to 4. At least that's what I planned. So the first array, transmit, contains the master transmissions to the slaves or to our slave. And the second array contains the data received back in the messages from the slaves, or currently our one slave. I also have here a constant timeout, which we will use later. It's currently set to 650 microseconds. Remember, that was the 500 microseconds for calculation and computing, plus 150 microseconds for the slave transmission itself. Back to the begin method. In that block here, I initialize the transmit 0 for our motor slave 0, setting the message address and then the motor data for the throttle and the motor data for the tiller, both to 0. Finally, I set the CRC. So we have now a valid master to motor 0 slave message here in transmit 0. I also initialize here the receive 0 array member, just setting all the data, so status, throttle, etc. to 0, so it all has a defined value. Next, we have a method set motor data, which is currently hard-coded to work on the transmit 0 array. And as an argument, it gets the throttle value and the tiller value and sets that throttle and tiller value inside the motor data. And finally, we of course have to recalculate the CRC for the whole thing. Then I have here a lot of functions of get motor status, get motor throttle, get motor tiller, which just return, again, hard-coded from received 0, the status, the throttle, and so on. And I really have such a method for each and every member of the motor struct, okay? Now we come to the core of things, the transceive method, which will transmit a message to our motor slave and receive its reply. If we successfully receive a reply, we will return true, otherwise false. First, I have here an RS-485 slave transmission receive, which will contain the reply from our motor slave. Then I have here a timeout time in microseconds. First, we set the data enable pin to high, enabling the transmitter, disabling the receiver. And then we transmit our byte array inside our transmit message. And I'm using here that size macro to calculate the size of the byte array. After a serial flush, just to make sure we transmitted everything, we set the data enable pin to low again, redisabling the transmitter, re-enabling the receiver. Then we calculate the time we should wait for the reply from the slave. That's of course micros plus our constant timeout in microseconds. And after that time has passed, we check for the number of bytes in our serial buffer. And if that's not the size of the reply we expected, then we empty the serial buffer and return false, and that would be it. But if we have received the correct number of bytes, we read them from the serial buffer into the bytes array of our receive union. Again, I'm using size here to calculate the size of the bytes array. And then, if the CRC is not correct, we return false at that point. If the address is not correct, we also return false. But if everything is fine, then we take the data portion out of our receive union here and assign it to our private member variable received 0. Which is of the type, message data. And we return true. In our master sketch, we now include that protocol.h file. We no longer need the timeout microsecond variable. That's now included in the master class. And we initialize an RS-485 master object, RS-485, by passing the 01 object and our data enable pin. In the setup, we no longer need to initialize that data enable pin and the 01 USART, because that's also done now by the begin method of our RS-485 object. In the loop, we no longer need our timeout time microseconds. That's now also included in the master object. And if we enter an input into the serial monitor, that is passed as before, but now we are using the setMotor data method to set our throttle data inside our RS-485 object. When the time for message exchange has come, we no longer need to do all the communication stuff by ourselves. That is now done by the transceive method of our master object. And if the transceive method returns true, we print out everything nicely formatted to the serial monitor, using all those get motor methods to retrieve the data we received. If transceive returns false, we simply print out to the serial monitor, motor didn't reply. That's it for the master. We are back in the protocol.h file and now looking at the class for our RS-485 motor slaves. Standard constructor is deleted as always, and our real constructor gets beside our hardware serial and the data enable pin also an RS-485 slave address. And we initialize some private member variables with that data. In the begin method, we initialize our data enable pin and our USART like we did in the master. And now let's have a look at the private member variables. Besides the stuff we already seen in the constructor, I have here an RS-485 slave transmission, transmit, which will contain the data we will be transmitting to the master, and an RS-485 master transmission message data motor, which contains the received data from the master for our motor. I also have here a constant timeout in microseconds, which I calculate using the constants we defined above down to the microsecond. Back to the begin method, where we initialize that transmit object with valid data including the CRC. And then, of course, we also initialize the received object with valid data. Like in the master class, we have a setData method where I can set all the parameters in our transmission. And of course, I also recalculate the CRC. So we always have a valid transmission to the master ready. There are only two get methods in the slave class to get the throttle settings received from the master and to get the tiller settings received from the master. The slave class has also a transceive method, which receives a message from the master and sends back a reply. If a message from the master is received successfully, it returns true, otherwise false. First, we have here an RS-485 master transmission receive, which again contains the message received from the master. And of course, we also have a timeout time microseconds. If there's nothing in the serial buffer, we immediately return false. That method is non-blocking. Otherwise, we calculate the time using micros plus our timeout microseconds until the largest possible message could be received. Please note that's a slave message. We could also receive a slave message. Then, after the time has passed, we check if the number of bytes we received is not equal to the size of a master message, which we are interested in. If that's the case, we empty the serial buffer and return false. Otherwise, we read the master message from the serial buffer and we check its CRC. If that's wrong, we return false. We check if we are addressed. If that's not the case, we also return false. And here I also check the contents of the message, if the values are in a valid range. If that's not the case, I also return false. After we're sure we received a valid message from the master, we set our data enable pin to high, getting our transmitter ready to transmit. And we write our transmit message, that is the bytes array, to the serial buffer. Again, using here that size macro to calculate the size of our bytes array. And again, please note, we have already a valid message in the transmit union. After the usual serial flush, we write a load to our data enable pin, getting our receiver back up and disabling the transmitter. And only then, we take the received message data motor and assign it to our received private member variable and return true. We do that afterwards so we can be sure we use the least possible amount of time before we reply to the master. To use the RS-485 motor slave class in our fly-by-wire electric outboard sketch, we include protocol.h and initialize an RS-485 motor object, RS-485, with our slave address motor 0, our serial 1 object, and our RS-485 data enable pin. Like in the master sketch, our setup no longer needs to take care of the serial 1 port and the data enable pin. That's now done by the begin method of our RS-485 object. In the loop, we no longer need that integer message that was storing that single byte old message from the master containing the throttle setting, and we no longer have to do all that communication stuff by ourselves. Instead, we use the transceive method, and if that method returns true, we use the getThrottle method to set a new value to our throttle set variable. And we also pass that same value to the throttle set method. In our display block, which is still updated every 100 milliseconds, I use the setData method to update all the motor data inside our RS-485 object, ensuring the master always gets up-to-date data. And that's it for the slave. Now, after the probably longest code walkthrough I ever did, for the anticlimactic result. So, yeah, here's our slave, no USB connected, we just have our RS-485 connection, slave is not powered, so like in the last video, we get motor didn't reply, and as soon as I power up the slave, we get data! Great! And you saw, maybe it's just happening again. We still have those transmission errors, and I intentionally didn't fix them because, yeah, it's very useful to test my code if I really can catch the transmission errors on our RS-485 line. But anyway, you see we no longer have any invalid characters or random characters in our messages itself. We are filtering that out now. But can I still set my motor to power? Ooh, yeah, 10%, great. 100%. Power, wonderful. Back to 0. And that's it. And that's it also for today. A quite strenuous video, I'll have to admit, but we had to go through all that protocol stuff at one point. The code is still not there where I want it to be, so there might be a continuation. But next time we will start with a redesign of our analog side of things around the analog to digital converter. Remember, we have that little nagging problem there that we put too much load on our reference voltage source. Till then, bye.